Okay, welcome class. Today we're going to start our review of the basic concepts before we get into the main topics of this course. And so we're going to start with the review sections R1 through, I believe, R7. And so R1 is where we're going to start, and that is sets. So we're going to talk about sets. What are sets? Basic definitions, operations on sets, how do we denote sets, and things like that. Okay, so this may be review for some of you, and it may not be review. It may be new for some of you, or maybe most of you. Those of you who have had different professors who have taught the class prior to this may have been introduced to these concepts. So again, just bear with me because it may be review, but nonetheless, it's good to review at times and to make sure that we haven't forgotten anything. So the basic definition. So a set is a collection of objects that, could be anything. It could be a collection of numbers. It could be a collection of um, cats. It could be a collection of shoes, a collection of cars, houses, whatever the case may be, people. Um, but in this case, what we're going to talk about is mostly going to be set of numbers. But in the general case, a set is just a collection of objects. Okay, the objects that belong to the set are called the elements or the members of the set. And we can denote a set by using these curly braces, okay, or just braces. And this is going to be important because without these braces, we don't have a set, at least denoted. Okay, so if you just write out 1, 2, 3, 4 with commas with no braces, then technically it's not a set, it's just a sequence of numbers. Okay, so don't forget, if you're talking about a set, don't forget the braces. Okay, so this here is a set containing the elements 1, 2, 3, and 4. Okay, and now the order of the elements rather, are not important. Okay, so I could have the same set denoted this way. Let me do this. Okay, where is... For some reason... Okay. For some reason I can't get the pointer. Here we go, tools. Okay, for some reason I can't get my highlighter. Usually I can get the highlighter, but oh well. That's fine. Okay, so as we do this, okay, so order doesn't matter. So whether I have 1, 2, 3, 4 or 4, 3, 2, 1, it represents the same set. So the order of the elements do not matter. Okay. Now to show that 4 is an element of the set, we use this symbol. It looks like a E. It's the sometimes we use the Greek letter epsilon, but it looks like an elongated E of sorts. But it means an element of. So if we say that 4 and we use the symbol, then we see excuse me. We are saying that 4 is an element of this set. Okay. Now we could also give a set a name. Okay. We could call this set S. We could call it A. Usually we use capital letters to represent a set. Okay. And so now 5 is not an element of the set, so we use the same syllable, we put a slash through it to mean not an element of. Okay. So now, let's go back. So now what we're saying is the set S, written as this way, we can use S to represent that set. So set S might also be described as the set containing the first 4 counting numbers. Okay. Now, there are other types of ways of describing a set too. There are infinite sets and there are finite sets. Okay, if we say F is a set, so we call set F consisting of all fractions between 0 and 1, well, that's an example of an infinite set because there are an infinite number of fractions that exist between 0 and 1. Okay? A finite set only has is a set that is not infinite. So it only has a finite number of elements or a finite number of members of the set. Okay? So the set comes to an end. Okay? There's only going to be so many elements. Now, some infinite sets can be described by listing. Okay, for example, if we want the set of the natural numbers, and we denote that with capital N, or what we also call the counting numbers, we can use n is equal to the first few numbers, right? The counting numbers are all of the numbers 1 through positive infinity, all the integers. And so we can say 1, 2, 3, 4, and then we can use what's called an ellipsis. These three dots tell us that this pattern goes on for infinity. Okay, or what it also means is it continues in like manner. Okay, so if we go 1, 2, 3, 4, and we have these three ellipses, then or this ellipsis, then what we do is we're saying that, hey, this continues on in the same pattern. Okay, now we also when we look at sets, we call this set builder notation. Okay, so when we use the curly braces, to represent a set, this is called set builder notation. So you're going to want to know this for future reference. This comes up all the time and will come up all throughout the course. Okay, so what set builder notation involves a variable that describes the elements of the set. Okay, the following set builder notation represents the set of 3, 4, 5, and 6, and is read the set of all elements x such that x is a natural number between 2 and 7. Okay, so if I say, and here's the set builder notation right here, if I write this, this means, hey, this is the set of all x such that, this vertical bar means such that, x, and then here's the rule, right? This is the rule that must be satisfied, or the criteria that must be satisfied in order to be part of the set. X is a natural number between 2 and 7. Well, what are the natural numbers between 2 and 7? Well, those are 3, 4, 5, and 6. So we can represent this set as just listing, right? This is called using the list method, right? We list out the elements. But if we have, and it's great for finite sets that are small, or we could use set builder notation, write it this way. Okay. Now, set builder notation comes in really handy when you're dealing with infinite sets. Okay. So here's an example. Okay. We want to identify each of the following sets as either finite or infinite. Okay. And then determine whether 10 is an element of the set. Okay. So if we look at this set here, we have 7, 8, 9, and then we have the ellipsis, which means it continues on in like manner, comma, 14. So these are all of the counting numbers from 7 to 14. Well, is 10 an element of this set? And the answer is yes. Okay. Now, what's going on with set B? Now, set B is a set, and it starts at 1, and then it goes to a 4th, and then it goes to a 16th, and it looks like the denominator is a power of 4. So 1 over 4 to the 0, which is 1, 1 over 4 to the first power, and then 1 over 4 to the second power, and then 1 over 4 to the third power, and then the ellipsis says, hey, this continues in like manner. So all of the elements of B, of this set, is of the form 1 over 4 to the nth power, where n is some integer from 0 to positive infinity. Okay, so now this is an infinite set. This is a finite set. Now this infinite set, well, what's going on? You start at 1, but all of these subsequent numbers, fractions, are less than 1. So this is getting smaller and smaller. The numbers are getting smaller and smaller and heading towards 0. So 10 is not an element of this set. And then, of course, C is in set builder notation. So we have to read it. This is the set of all x such that x is a fraction between 1 and 2. Well, is this an infinite or finite set? Well, very much for the same reasoning that all fractions between 0 and 1 is an infinite set, so is this set. And in fact, anytime you're looking for the number of fractions between two consecutive counting numbers, you're going to have an infinite set. Okay? And of course, 10 is not in this set because 10 is outside 1 and 2. And all we want are the fractions that are between 1 and 2. Okay? And so then D, again, here is set builder notation. So we're going to read this as x is the set, or excuse me, this is the set of all x, such that x is a real number between 9 and 11. Well, there are lots of real numbers. In fact, there are infinite real numbers between 9 and 11 because a real number is anything that's a decimal, okay, or could be written as a decimal. And so 10 is also a real number that's in between 9 and 11. So 10 is an element of this set as well. Okay, so here are the solutions. Now, what about example 2? It says use set builder notation or set notation and list all the elements of each set. Okay, so this says we want the set of all x such that x is a natural number less than 5. So natural numbers, where do natural numbers start? So natural numbers are the counting numbers, and you always count starting with 1. So natural numbers always start with 1. So these are all the natural numbers that are less than 5. So this would include the numbers 4, 5, 1, 2, 3, and 4. Okay, right here. And remember, we have to have the braces. Okay. Then B says the set of all x such that x is a natural number greater than 7 and less than 14. So 7 is not included and 14 is not included in this. So it's all the natural numbers between 7 and 14. So this would be 8, 9, 10, 11, 12, and 13. So this would be the set. Okay. Now, when we're discussing a particular set, particular situation or problem, the universal set, whether it's expressed explicitly or not, contains all of the elements included in discussion. So we use the letter U typically for the universal set. The null set, or what we call the empty set, is the set that doesn't contain any elements. Okay? So there's a couple of ways we can represent that. We can represent that with the symbol of the circle with the slash through it, or we can use the braces with nothing inside. Okay, either way it's the same thing. But what we don't want to do is use this symbol here. Okay, this is not the null set. We're basically using two symbols. Okay, it is a set that contains the null set, or containing the symbol. So do not combine these symbols. Okay, so just be careful with that. Okay, now every element in the set S, which is 1, 2, 3, 4, is a natural number. So S is an example of a subset of the natural numbers n. Okay, now how do we represent a subset? By using this symbol here. This means that it means subset. Okay, so if we want to take this set and represent a subset of the natural numbers, we would just say S, use this symbol, n. And so what this means is S is a subset of n. Okay, now, by definition, set A is a subset of B if every element in E is also an element in B. So just the way we would think of a subset, okay? So if A is 2, 5, and 9, and B is 2, 3, 5, 6, 9, and 10, then we can see that 2, 5, and 9 is also elements of B. So since each element of A is an element in B, A is a subset of B, okay? But B is not a subset of A, okay? So A is a subset of B, but B is not a subset of A because not all of the elements in B are found in A, okay? And we use the slash, of course, for not a subset. Okay, typically in mathematics or logic, we use the slash to mean not, okay? Typically more in mathematics, we use this symbol for not a subset or not an element in the case as we were talking before. Now, here's a couple of things you definitely want to remember is that every set is a subset of itself, right? And the empty set is a subset of all set or every set, okay? So if A is any set, then A is a subset of itself, and the null set or the empty set is a subset of A. Those are always true. Okay, now, how do we show a set, the relationships between sets? Well, we can use what's called a Venn diagram, okay? So figure 1 shows that A is a subset of B because A is the smaller circle, and it's inside the set B. So we can represent using this visual called a Venn diagram. So this box here represents the universal set, the set of all objects that we're considering. A is a set of another set of objects, and B is another set of objects. And so A in this case is a subset of B. Okay. Now two sets A and B are equal whenever A is a subset of B and B is a subset of A. If this is true, then we say that the two are equal. Okay, now equivalently, we would say A equals B if the two sets contain exactly the same elements. For example, if we have 1, 2, 3, and we have the set 3, 1, 2, remember order doesn't matter, all we care about is what elements are inside the set, you can see that these two sets are the same and therefore equal. Okay. Now also we could see that these two sets here are not equal because they don't have the same number of elements. So one thing we could use is the fact that if we have two sets that are not the same size, that do not contain the same number of elements, they can't be equal, right? In order to be equal, you have to first be of the same size. In other words, you have to have the same number of elements. Okay, now that's not good enough. Okay, just to have the same number of elements though, right? You can have two sets that are the same size but are not equal. So you got to be careful with that. Okay? So in this case here, these are not the same. Okay? And of course, we can see that 0 is not an element of the first set, so therefore they can't be equal. Okay, so now here's example 3. Okay, now, so we're going to let U equal this set. A is going to equal this set. B is going to equal this set. C and D are going to equal this set. Okay, so we just have to be careful with that. Okay, so what we're going to do is we are going to look at A, D. We're going to determine whether these are true or false. So D is a subset of B. Well, how do we determine whether the D is a subset of B? If all the elements of D are also an element in B. So D is 1 and 9. So all we have to do is look at B and see if 1 and 9 are both elements of B. And indeed they are. So this is true. B is a subset of D. Well, B can't be a subset of D because they don't have the same number of elements. So obviously this is going to be false automatically. Okay. And then C is not a subset of A. Well, in order to show that C is not a subset of A, we either need to show that C is bigger than A, or at least one element of A is not in, excuse me, one element of C is not in A. So if we look at C, 3, 9, and 11, A is, well, 3, 9, and 11 are in there. So C is actually a subset. So this is a false statement, okay, because 3, 9, and 11 are in A. So C is actually a subset of A. So this is false. Now, U is equal to A. Well, in order for this to be true, we have to show that all the elements of U are in A and all the elements of A are in U. Okay? Well, are they? So this is 1, 3, 5, 7, 9, and 9, 11, 13. Well, this is missing 13. So since 13 is not in here, these are not equal. Okay? So it's false. Example 4. Let U equal this set, A equal this set, and B equal this set. Okay, so let's look at A prime. Oh, this is a good one. A prime means that it's a complement of a set. Okay, so operations on sets. So a complement of a set is all the elements that are not in that set. Okay, that do not belong to that set. So A is the complement of all the elements that do not belong to A is the complement of A. And we represent that as A prime. Okay. So this represents what we call the complement of a set. Now, we could also use the set builder notation. Because remember, we're going to say that using set builder notation, we're saying, hey, we want the set of all x such that x is an element in the universe, but x is not in A. And using the Venn diagram, we can see that the complement of A is everything outside the set of A, right? So again, using the definition of a complement, we can see using the Venn diagram as a visual, the set builder notation, we can see the same thing, or symbolically as A prime. These all mean the same thing, okay? So we want everything that's, all the elements that are not in the set A. That's the complement of A. Okay, so if we use these and we want the complement of A, well, we want everything that's in the universe, but not in A. Well, we don't want 1, 3, 5, and 7. Okay, so if we eliminate 1, 3, 5, and 7, what does that leave us? 2, 4, and 6. So A complement is the set of 2, 4, and 6. Right here. Okay, B prime. Well, B prime is everything that's not in B. So the complement of B is everything that's not in B. So B is 3, 4, and 6. So we want everything that's in the universe, but not in B. So that would mean that we want everything except 3, 4, and 6, which would mean we want 1, 2, 5, and 7, which would be that. Now, what's the complement of the empty set? Well, the complement, well, if the empty set is nothing, then the complement of the empty set must be everything. Okay, so that means it would be U. So the complement of the empty set is the universal set. The complement of the universal set is the empty set, because the universal set has everything. If you want the complement of everything, that's nothing, right? Okay, so now let's look at the intersection of two sets. So A and B are sets within the universal set, okay? The intersection of the two sets is given by the symbol of the upside down U. It looks like an upside down U. A intersect B is everything that's in both sets. So the intersection of A and B is everything that's in both A and B. So if we look at A being 1, 2, 4, 5, and 7, and B being this set, and we want the intersection of those two, then we want the intersection of this set and this set, which is everything that's in both, which would be 2, 4, 5, and 7, which then would just be this set. So the intersection of two sets, again, are all of the elements that are in both sets. Okay, and we can extrapolate this to 3 sets, the intersection of 3 sets, 4 sets, and so on. Okay, now if we look at the Venn diagram, the intersection is the shaded region. Okay, the overlap. Okay, so we can look at that. Or if we look at the intersection symbolically as set builder notation, we can use the set of all x such that x is an element of A and x is an element of B. Okay, now, if the two sets have no elements in common, we call them disjoint sets. And we represent them as two circles that are not overlapping. Okay, meaning disjoint, right? Two circles that are disjoint, they don't overlap. So two sets that do not have any elements in common are called disjoint sets. Okay? And so if that's true, then the intersection is going to be the empty set. For example, if we use the set 50, 51, and 54, and we use the other set 52, 53, 55, and 56, well, these have no elements in common. So the intersection of these two sets would be the null set. Okay? Okay, so now let's look at each set. Let's identify these sets as if they're disjoint or not. Okay, so do these have anything in common? Yes, they do. 15 is in both. So we know that these are not disjoint sets. What about B? Do they have anything in common? Yes, they have 2 and 3. Well, they have multiple things in common, but you only need at least one, so 2. So they have things in common, so there is an overlap, so these are not disjoint sets. What about these two? Well, these are odd and these are even, so obviously there's nothing in common here, and these are two disjoint sets. Okay, now, if we look at another relationship between two sets, we call this the union. Okay. Oh, by the way, notice if we go back to the intersection, notice that the key word that we have here is and, right? We want to know that what's in A and B, okay, in both, right? So it's either in A or B or in both, okay? Or excuse me, that's or. But in the intersection, it's A and B. Okay, so it's an and statement. But if we go down to the union, well, here we look at an or, right? We want to know if the elements belong to A or B or to both. So the union of two sets means that we're going to pool all of the sets together and get rid of any duplicates. Okay, so we're basically going to pour them in the same bucket and then get rid of any duplicates. So we're basically putting them together. Okay, so if we want the union of two sets, meaning union, we put them together, right? We bring them together as one, right? So if we want the union of A and B, we say A is equal to 1, 3, and 5, and let B equal 3, 5, 7, and 9. Then if we take the union of them, we're going to pool these together and then get rid of the duplicates. So we end up with the set 1, 3, 5, 7, and 9. Okay, so we don't end up with 2 3s and 2 5s, right? We get rid of any duplicates. Okay, now the Venn diagram means that, hey, look at that, everything is shaded. If we take the union of two sets, that means we're taking everything in A or everything in B or both. So we get everything in both sets. And so in set builder notation, we can also represent it as AUB, right? A union B. And we can write it as set builder notation. X is the set of all X that is in A or X that are in B. Okay, so here's example 6. Okay. So here we have two sets and we want to know, find each of the following, right? So we want the union of these two sets. So again, we're going to pool these together and get rid of any duplicates. So our result is going to be 1, 3, or excuse me, 1, 2, 3, 4, 5, 8, 9, and 14. And so we get 1, 2, 3, 4, 5, 8, 9, and 14. That's the union. Okay. Now here we're going to use the union of these two. We're going to, again, pull them together and get rid of any duplicates. So here we're going to get 1, 2, 3, 4, 5, 6, 7. So we're going to get all the numbers 1 through 7. And then here we're going to take all of the numbers. Now what's going on here? Well, what does this set represent? We have the ellipses. So we've got all of the odd natural numbers. And here we've got all the even natural numbers. And so if we put all of these together, what do we end up getting? Well, we end up getting all the natural numbers. So we just write n. So notice that we don't have to write out the set notation with 1, 2, 3, 4, 5, 6, 7, and the ellipsis. We could, but if we use the symbol n representing the natural numbers, we can just use the symbol. And that's totally fine to do that. So here are the set operations. Okay, so we're going to let A and B define a set and U is the universal set. The complement of A is used A prime, and it represents all elements in the universal set that do not belong to A, and we represent it this way. Okay, the intersection of sets A and B, written using this symbolism, is made up by all the elements that belong to both set A and set B. And we can represent it this way. And then the union of sets A and B, written A union B, is all the sets that are either in one set or the other set or in both. And we don't have to write the both part, but we basically write it this way. Okay, and that is the end of Review 1 or R1. And so next time we'll start with R2 and we'll go on further with regarding sets and things. Okay, until next time, have a great day.